Hi everyone, thanks for inviting me to the L2ID workshop. I'm Xiuye, a research engineer from Google Research. Today I'm going to talk about our recent work on open vocabulary detection and segmentation. First, I'd like to introduce a little bit about open vocabulary visual recognition. Open vocabulary visual recognition is very different from traditional visual recognition problems. It recognizes categories described by arbitrary text queries, which is far beyond the closed set categories in the training set. Since there are abundant image and text pairs available on the internet, people utilize these cheaply available image and text pairs to advance the field of open vocabulary classification. One milestone is the CLIP model from OpenAI. They collected 400 million image and text pairs and jointly pre-trained an image encoder and a text encoder using contrastive learning. Specifically, the model learns to predict which out of a batch of sampled texts is actually paired with the input image. After pre-trained on the very large-scale dataset, CLIP achieves amazing performance on downstream classification tasks. For each candidate category, they use a prompt template, a photo of the category, for example, a photo of a dog, as the text query. The predicted category is the one that is the most similar with the input image in the joint embedding space. This approach achieves 76.2% top-1 accuracy on ImageNet. This result is comparable with a fully supervised ResNet 50 model, but CLIP is not trained on the ImageNet training data at all. Concurrently, there is also the Align model from Google. Align uses a larger and noisier image and text dataset. Their approach is very similar to CLIP. In addition, they evaluate on several retrieval benchmarks and achieve very good results. So now that there are these very powerful open vocabulary classification models, we wonder if we can also add open vocabulary capacity in other vision tasks, for example, detection and segmentation. But unlike image classification, we don't have paired text and object or segment cheaply available on the internet, so we need to design some specific techniques. So the first project I'd like to talk about is WILD, Open Vocabulary Detection via Vision and Language Knowledge Distillation. This is a joint work with Zhongyi, Weichen, and Yin. So the research community are collecting detection datasets with more and more categories to enable large vocabulary detection. The very recent LVIS dataset marks a peak of such effort with more than 1,200 categories, and it is also the main dataset that we evaluate on. In natural images, object categories follow a long-tail distribution, which is also called the zip-fence law. To find sufficient training examples for rare categories, people need to collect significantly more data. The figure on the right shows the sorted number of instances per category for the LVIS dataset. We notice that a very large number of categories have less than 10 instances. So it can be very expensive to scale up the detection vocabulary because people need to manually label the categories, the bounding boxes, and sometimes the instance masks. This makes us think, are there any alternatives for large vocabulary detection? So we propose open vocabulary detection as an alternative approach for large vocabulary detection. And in open vocabulary detection, it solves this scenario. So you have a detection dataset with the label toy. However, your users want to detect toys of different colors and types. Fully supervised detectors can only detect objects of the predefined category list, and you have to collect data for the new labels and retrain the model every time you need some to detect new categories. Open vocabulary detectors, on the other hand, can detect objects described by arbitrary text inputs. And it serves as a new direction for large vocabulary detection. Instead of collecting these costly annotations for the rare categories, it also changes detection categories during inference time without the need of retraining. Given the great success in open vocabulary classification, we propose to borrow the knowledge from open vocabulary classification models for open vocabulary detection. And we decouple the detection problem into the localization problem and classification problem. For localization, we found class-agnostic modules generalize well to novel categories after training on enough number of categories. For classification, we distill the knowledge from a pre-trained open vocabulary classifier into a two-stage detector. In our experiments, we used the mask RCN standard detector. And we mainly use OpenAI's CLIP model, as mentioned before. And note the two yellow circles here. We leverage these pre-trained text and image encoder in the wild training. So now let's take a look at the architecture. Wild uses the same backbone architecture as the standard mask RCN architecture. Most of the changes happen in the detection head. So on the left, we show the standard faster RCN head. For each object proposal, we compute a region embedding, which is the input to the classification layer. And in the middle figure, we are incorporating the CLIP's pre-trained text encoder into the architecture and use the knowledge from this pre-trained text encoder. So we use CLIP's text encoder to encode the category names into text embeddings and use them to replace the learnable classification weights. For the background category, because it's a bit hard to find some word to describe all the background categories. So instead, we still use a learnable background category. And the region embeddings are now trained to align with the text embeddings. Or in practice, we simply treat these text embeddings as a classifier because to compute the cosine similarity between text embeddings and region embeddings after normalization, it's just a dot product, which is the same as the learnable classifier. So you can think these text embeddings as a classification layer, but they are not trained. They are always fixed. And because the pre-trained text encoder encodes the text embeddings on a semantic space, so this method can generalize to novel categories, even though the model is only trained on the base categories. Oh, by the way, so during training, we have base categories available for train, but we hold out a set of categories which we call novel categories, and they are never seen during training. So for the middle figure, we call it wild text. And on the right, we also distill the knowledge from the pre-trained image encoder from clip. So we train the region embeddings in the detection head to be similar to the image embeddings of the cropped regions. The image embeddings of the cropped regions are computed offline. We first crop and resize the pre-computed region proposals, feed them into the pre-trained clip image encoder to obtain the image embeddings. We call this method wild image, and this knowledge distillation is trained with an L1 loss. Wild is the combination of wild text and wild image. We train the detector with these two learning objectives. Here is an overview for wild. We apply the text prompts to all categories and feed them into the pre-trained text encoder. The text embeddings serve as the fixed classification layer during both training and inference time. For inference, we also include the text embeddings of novel categories. And the wild image distillation part is discarded after the training is done. During inference time, the network architecture is very similar to the original two-stage detector, so we are not increasing the inference speed. Here are some quantitative results on LVIS. We mainly evaluate on the LVIS dataset, the detection dataset with more than 1,200 categories. And we hold out LVIS rare categories as novel categories, which are never seen during training. And we also use the AP on the novel categories as our main metric. So here we show the results on ResNet 152 backbone. Wild outperforms the supervised baseline. And when using a stronger align model as a teacher model and a stronger EfficientNet B7 backbone, the performance of Wild is even close to the fully supervised 2020 challenge winner. And here we show some qualitative examples of the detected novel objects. We find not only the classification is correct, the masks also have high qualities in general. And besides the performance on the novel categories, Wild also can do Finetuning-free transfer. After training on LVIS, we directly transfer Wild to other detection datasets without any fine-tuning. All you need to do is to replace the text embeddings from the LVIS text embeddings to the target datasets categories text embeddings. And we evaluate on Pascal VOC, COCO, and Object 365. They are all popular detection benchmarks. The AP and more results are listed below. So the performance is still have a little gap compared with the fine-tuning method or the fully supervised method. But the gap is not that large given that we are not doing any training on these datasets. And on the bottom, we also show some qualitative examples for the fine-tuning-free transfer. Wild even have more capacities, so you can use free-form text to interactively recognize more details for the detected objects. We simply calculate the cosine similarities between the region embeddings and the freeform text embeddings. On the left, Wild is able to distinguish between fine-grained dog species, and these dog breeds do not exist in the training set. On the right, Wild also recognizes the colors of different bird body parts. And we are using some complicated text here, and Wild still shows the correct results. And start from the previous examples, we can do a systematic expansion of dataset vocabulary using a similar approach. So in the example below, we made a color attribute set with 11 colors and expand the LVIS vocabulary with these colors. The method is simply appending the color attributes to each original category so that we expand the LVIS vocabulary size by 11 times. The left figure shows the detection results on the original dataset vocabulary, and on the right, we show the results after expanding the LVIS vocabulary with the 11 colors. We show that Wild performs really well on detecting these color attributes, and most detection datasets do not have the object attributes annotation. Our method shows a simple way to systematically detect object attributes. So next, I'll talk about our second project in the open vocabulary field. And this time we explore the image segmentation task. This is a joint work with GoNet, In, and Zhongyi. It's accepted to this ECCV. You are more than welcome to join our poster session. And we call this method OpenSeg. So in open vocabulary semantic segmentation, our goal is to segment images with arbitrary text queries. And when given different lists of text queries, the method should organize the image differently. So in this picture, we show the qualitative results of OpenSeg on different text queries. So if there are less categories, the organization of the segmentation is simpler, and OpenSeg is able to do this. So similar to Wild, the model first learns to propose class-agnostic segmentation mask proposals for possible organizations. And here we are using a different method for the class-agnostic proposals. Different from Wild, we don't use an RPN, but instead we use a cross-attention module between the image features and some learnable queries to generate a mask proposal for each query. And this approach is pretty similar to mask former, since we also train on image text data which do not have the segmentation annotation. So we first generate pseudo-labels for these images without the segmentation annotations. Here we show a qualitative example of the predicted class-agnostic segmentation mask proposals. OpenSeg is able to segment an image into meaningful regions. We observe a strong generalization ability in this class-agnostic mask proposal module. The training data of COCO, which is the data that we use to train the mask proposal module, do not have underwater scenes, but the model is still able to segment the underwater scene into these meaningful proposals. And after the class-agnostic mask proposal module, OpenSeg then learns the visual-semantic alignments by aligning each word in a caption to one or a few predicted mask proposals. In particular, we break the image into the region proposals, and then use the predicted mask proposals to pool the image features to get a feature for each proposal. We also break the caption into words. More specifically, we extract all the nouns and adjectives inside the caption, and then we obtain the text embeddings using the align text encoder. We then use a grounding loss to learn the region and word alignments from weakly-supervised image caption data. The grounding loss is similar to contrastive learning on region and word pairs. Unlike per-pixel segmentation, the mask proposal representation supports weakly-supervised learning and also makes the method more scalable on image text data. So here shows how we perform the weakly-supervised visual-semantic alignment. We extract the nouns and adjectives from the caption, for example, the dog and surfboard from this caption. And we align these words with the predicted mask proposals. So for the grounding loss, we compute the similarity score using the alignment scores of the regions and words. And because of our mask proposal module, we are able to do the weakly supervised learning on proposal level instead of pixel level. This makes the method more scalable on image text data, because we don't need to know the label for each pixel. We only need to know one label for each proposal, which is the middle level image representation, and which is simpler. So here we show 3 different neural network architectures for comparison. On the left, it's the architecture for the align and clip models, or in general the open vocabulary classification models. They do an image text contrastive learning. The drawback is that they use a one-dimension vector to represent the whole image and throw away location information. In the middle, we show per pixel segmentation, which requires class-specific mask annotations and is not very scalable. The architecture of OpenSeg is shown on the right. OpenSeg represents an image with a set of segmentation regions, and then it enables weakly supervised learning using image captions. So here we extract the text embeddings for the words in the caption. And here, after the backbone, the cross-attention module, we obtain the mask proposals through the cross-attention modules, and they are supervised by class-agnostic segmentation annotations. After learn these mask proposals, we use these mask predictions to pool the features for each mask, and then we apply the region to word grounding loss. So here we show the zero-shot transfer results to other datasets. OpenSeg is trained on COCO and Localized Narrative dataset. We directly transfer to the AD20K Pascal Context and Pascal VOC segmentation datasets. OpenSeg generalizes better than LSeg and LSeg Plus. The LSeg Plus is trained with COCO labels. OpenSeg also outperforms group VIT and previous zero-shot methods. This is some qualitative results. Comparing with other methods, Align has very low resolution because it's a classification model. And when trained on more data, when we add the localized narrative datasets, we get better performance for OpenSeg. This shows that OpenSeg is scalable. And in summary, we explore two downstream open vocabulary tasks, VILD for open vocabulary detection and OpenSeg for image segmentation. And in these two projects, we also explored two very different approaches to learn the open vocabulary capacity for these dense visual prediction tasks. So in VILD, we use a distillation method that distillations the knowledge from a pre-trained open vocabulary image classification model. And in OpenSeg, we use weakly-supervised learning on image text dataset to learn the open vocabulary capacity from the image text data. And both approaches decouple localization from classification. The localization learned from class-agnostic modules because we found that class-agnostic modules generalize well to novel categories after training on sufficient categories and sufficient data. Also, please feel free to try out our demos. Both VILD and OpenSeg has a open source version on Clip. So thank you for listening, and I'm happy to answer any questions.